So we're spending a lot of time talking about mathematical circular convolution. We don't want mathematical circular convolution. I'm only talking about it because I want to explain what MATLAB gives you. What you want is linear convolution, right? Because that's our output. If you know our input, if you know the impulse response, linear convolution is the output. So how do you get that using DFTs? That's the moneymaker. How many operations does this thing take? This takes, unlike regular convolution, where you've got n of these for every output value of y, well, you've got 2 times n minus 1, but it's of order n of these for your different values of y, and each summation has got order n pieces to it. So your whole thing your whole regular convolution is of order n squared. It's exactly 2 times n minus 1 times n, but it's order n squared. You know the DFT is only order n log n, which really big n's is almost linear in n. This thing is order 3 times n log n, which is still n log n. If you want to find the output, linear convolution, the way to do it is to somehow use these DFTs to cut down your time. But how do we do it? Anyone want to give me a guess? The problem comes in this step. Intuitively, the problem comes down here when we have to time alias things down. And if only we didn't have to time alias it down, if only our thing down here didn't have 3 steps, but it had 5 things, then we wouldn't need to time alias anything down. So what would we have to make our inputs look like if our output has 5 steps? How long would they have to be? Garrett?
It'd have to be 3 because it's 2n minus 1.
Yeah, so if these 3 convolve with these 3, will definitely give us 5. But if we want to avoid this, if we want to have our circular convolution equal our linear convolution,
would you zero pad it, sir?
You'd zero pad it. That's it exactly. And how far would you zero pad your inputs? How much zero padding would you give to this guy?
2.
2. And we'd zero pad this thing by 2. We haven't changed our signal at all, but now when we do our inverse DFT of the product of our individual DFTs, we'll end up having to have the exact same linear convolution is the same, but now because there's 5 spots, there'll be no time aliasing. So the secret is to zero pad your X's and your H's to make them NX plus NH minus 1 long. And with that insight, now we can handle X and H's of completely different lengths. So specifically, you'd want to zero pad your new X, I'll call it X1, to equal your own old X, and then you'll put your zeros of this minus your NX, so NH minus 1. And you'll want to zero pad your H1 to make it equal to your old H, with enough zeros to also make it NX plus NH minus 1. So if it already has NH, we'll want to pad it by NX minus 1. And now you can take those DFTs. Now we can say that your Y1 is equal to your inverse FFT of your FFT of your X1 dot times your FFT of your H1. And this will be now of length, same as the lengths of all of these, which will be of length NX plus NH minus 1. And it just does the right thing. And the cool thing is that this is now screamingly fast. And it doesn't make a difference when you're dealing with lengths of 100, But when you're dealing lengths of a billion, it can make the difference of finding out a solution in a couple of minutes versus several years. All right, questions about any of this?
So what was the whole point of zero padding again? Just to make the process faster?
Yeah, here it is. Good question. So what?
Wait, sir. Is the point of the zero padding so that we don't have to do that addition that you have written in red on the left?
That's exactly right. So we don't have that time aliasing. So the whole point of what we covered today, the whole point of today's lesson is that circular convolution is bad. We don't want it. It does not help us at all. I can't think of a single reason why you would want to circularly convolve two signals, but it's easy to perform. And by easy, I mean it's fast, it's efficient. You do this using the FFT algorithm, it's really, really fast. Now, if you weren't using the FFT algorithm, if you're using the DFT algorithm, don't. It's awful. There's no reason the DFT algorithm doesn't let you compute the straightforward implementation of the DFT algorithm using the summation with the complex exponentials. It doesn't give you any advantage to just performing the old-fashioned direct linear convolution. In fact, it's worse because now you're working with complex exponentials, and the old-fashioned convolution just has you flip one and then shift and add these real things. You can do it graphically, it's fast. But if you're dealing with really long sequences, FFTs are incredibly faster. I mean, the difference between doing things in minutes and doing things in years when they get long. So by zero padding, we get the usefulness of regular linear convolution with the speed of using the FFT algorithm. And that's the point of all this. And in the lab coming up, you'll be experimenting using MATLAB's built-in conv command, which does linear convolution, which is order n squared. And then you'll also be comparing it to how fast you can build your own convolutional kernel that uses FFTs to do it this more complicated way. And you'll find it screamingly fast. This is totally not obvious, right? It just makes total sense that, hey, we could convolve these things linearly just using our heads. I mean, just obviously, this is super easy to do. Zero padding them and then taking DFTs of these things, which is complex exponents, and it just seems obviously so much more complicated. So this is completely non-obvious how, for long signals, this is the way to go. This is so much faster than just using the straightforward linear brute force algorithm of convolution. Any other questions?
Sir, when you were setting up the vector for x1 and h1 in your example, in this case, nh and nx, big N of h and big N of x would be the same length, right? Because
in this example, yes. And then over here, where I give you how to actually implement it in real life, now it's generalized. Now nx can be anything. Let me give you a quick example. So you've got x equals 1, 2, 3, and you've got h equals 2 and negative 2 and negative 2. So you can convolve these two, x and h, to get this. And just a quick check, 3, length 2, 2 plus 3 is 5, minus 1 is 4, 1, 2, 3, 4. That makes sense. This is the sum of the two input lengths minus 1. So now let's see what would happen if we naively took an inverse FFT of the FFT. We can't even take the FFT of x and multiply by the FFT of h because they're different lengths. And that will give us an error. But if we pad them, if we pad x with, we want to make it length 4, it's length 3, so we're going to pad it with 1, 0. And to that, we're going to multiply it by the zero padded h. And it's currently 2. We want to make it 4, so we're going to zero pad it with 2 zeros.
You're missing a parentheses after the x vector,
There we
after
go.
the 0.
Yeah, let's try that. There we go. And this gives us our same answer as our original. Does that answer your first question for us?
Sir, yes, I think you answered both. I'm just trying to see the n of h minus 1 and n of x minus 1. Where that would apply.
So the n of x is equal to the length of x. The n of h is equal to the length of h. So therefore, our answer should be the length of the convolution should be the same as always n of x plus n of h minus 1. And it is.
I see, sir. Thank you.
Yep, you bet. Any others?
So, how are we supposed to be dealing with indexing when we're doing these problems? Like, what if x and h both don't start at index 0?
Right. So to do that, there's nothing new with linear convolution than what we already spoke about. So to go back to our earlier lesson when we talked about how to deal with things when they don't start at 0. And you can do that to create the indexing. If x and h begin at n sub x1 and n sub h2, then y will begin at their sum. And I've got some examples about how to do this back in our lesson 6. Does that answer your question?
Yes, sir. Thank you.
Yeah, you bet. Any others?
So, sir, MATLAB, when you use the convolution command, they're doing linear convolution.
Yes, that's exactly right.
Is there any reason why they don't just build this into the convolution commands?
Broadest answer is that if you're doing short convolutions, it's pretty clear that graphical is the winner. But when you're doing really long ones, that order n squared thing just kills you. So let me give a practical example of how this works on MATLAB. Let's create a random variable, a random vector x. And we'll say it's 2 raised to the 19th power in length. So it's pretty large, right? That's 500,000 samples. And I'll do the same thing I'll create an h vector that's the same length. So here are 2 vectors in the upper right. Input, impulse response, each roughly 500,000 in length. I'm going to measure how long it takes to convolve these 2. Takes a moment to do this linear convolution. So in the background, MATLAB is performing a linear convolution, which is on the order of n squared operations. And you can see it took 11 or 12 seconds to do this for a 500,000 input length. Now watch how long it takes to do the convolution using FFTs. Wow. So the difference in ratio was 933. So the difference as a ratio is that the FFT method, the DFT method rather, took well under 1% of the time that it took a linear convolution. And that difference only gets larger as the length of your inputs increase. And for finding small signals, it's not at all uncommon to be working with signals in the order of 1 million long.